don't often consider water as a nutrient, it is without a doubt the most important nutrient we consume. We can survive 40 days without consuming food and years without some vitamins. However, we would only last 6 to 8 days without water. Water makes up more than half of our total body weight, and it is involved in virtually every biochemical and physiological function in the body, including a heat conduit for temperature regulation, a transport medium for blood, a lubricant and cleanser, a medium for chemical reactions, and maintenance of acid-base balance. It is important for the body to maintain a general fluid balance in order for homeostasis to occur. General fluid balance can be explained as the difference between the amount of fluid taken in and the amount of fluid excreted. Fluid leaves the body in two ways: sensible and insensible loss. Sensible loss is fluid loss that can be measured. Examples of sensible loss include loss through urination, defecation, or wound drainage. Insensible losses are those that cannot be measured or seen. Examples include loss through evaporation from skin, such as perspiration, and from lungs. Sweat is one method in which the body loses water. Exhaling leads to loss of water via vapor. During physical exercise, both routes have a purpose. Perspiration helps to keep the body cool, and moisture in the air we breathe helping to keep the mucous membranes moist. When there is excessive loss of fluid through perspiration and heavy breathing, dehydration can become a problem. Fatigue is an early first symptom of dehydration. A water loss of even 1 to 2% of body weight can lessen a person's capacity to do muscular activity. A 7% loss can lead to a likely collapse. Working muscles produce heat as a byproduct of ATP breakdown. The body cools itself via sweating. Each liter of sweat dissipates about 600 kilocalories of heat, preventing a rise in body temperature of almost 6 degrees Fahrenheit. The body routes its blood supply through the capillaries just under the skin, and the skin secretes sweat to evaporate and cool the skin and the underlying blood. The deeper body chambers are cooled when the blood flows back. When a person sweats, a small amount of electrolytes are lost from the body along with the water. Electrolytes are substances that, when dissolved in water, gives a solution that can conduct electricity. The major electrolytes, sodium, chloride, and potassium, are essential to life. The major function of electrolytes in the body is to serve as an electrical medium. To this end, their primary role in the body is the conduction of nerve impulses within neural tissue and muscle. The relay of information from the nervous systems to our tissues and organs is necessary to live. The heart won't beat, muscles won't contract, and digestion stops if nerve impulses are prevented. Thus, it is important that the human system have a highly regulated mechanism that maintains the electroconductive capacity within the body. This capacity is maintained through the regulation of electrolyte balance. Electrolytes are compounds that have a positive cation or negative anion charge and conduct the electrical impulses within the body. They are distributed in such a way that within a given compartment, electrical neutrality is always maintained and the anion concentration exactly balances by the cation concentration. In today's program, Fluid and Electrolyte Imbalance and Overview, we'll be reviewing the fundamentals of fluid and electrolytes as well as discussing acid-base balance within the body. In the syllabi materials, we discuss what we just reviewed regarding the importance of maintaining equilibrium of electrolytes, fluid and pH levels, but we also discuss the distribution of fluids within the body, the mechanisms for maintaining fluid balance, and the various functions of the electrolytes. During this portion of the program, I will describe the difference between acidosis and alkalosis and describe the mechanisms for maintaining pH balance. Let's review what you've learned regarding the distribution of fluid within the body. It is essential that we understand how the fluid is distributed and how easily the equilibrium can be disrupted, for example, by fever or illness. It's not an exaggeration to suggest that our bodies are mainly water. Water makes up over 60% of our total body weight, with the remaining percentages distributed mainly among proteins, lipids, and minerals. Body fluid is distributed between two compartments, intracellular and extracellular. Intracellular fluid is that which is located within the cell. It accounts for approximately 2/3 of the total body fluid and 42% of body weight. Extracellular fluid is that which is located outside the cell. In an adult, extracellular fluid accounts for 1/3 of total body fluid and 20% of body weight. Extracellular fluid is further broken down to interstitial, intravascular, or transcellular compartments. Intravascular fluid is contained within the blood vessels, and it contributes to approximately 5% of body weight. It is responsible for maintaining blood volume and perfusing tissues and cells. Interstitial fluid lies between the cells and includes lymph vessels. It accounts for 15% of body weight. Finally, transcellular fluid is contained within a space that is separated by a layer of epithelial cells. It includes digestive juices, synovial fluid, intraocular fluid, cerebrospinal fluid, and urine. In order for homeostasis to occur, water must be balanced throughout these compartments. Water intake must balance water loss. To maintain water balance and to protect against dehydration and other medical problems, healthy adults should drink at least 1.5 to 2 quarts of fluids a day. The body obtains water primarily by absorbing it from the digestive tract. Additionally, a small amount of water is produced when the body metabolizes certain nutrients. The body loses water primarily by excreting it in urine from the kidneys. Depending on the body's needs, the kidneys may excrete less than a pint or up to several gallons of urine a day. About 1.5 pints of water are lost daily when water evaporates from the skin and is breathed out by the lungs. Usually, a person can drink enough fluids to compensate for excess water loss. Within the water must be a balance of the electrolytes. The main electrolytes discussed in the handout include sodium, potassium, calcium, magnesium, and phosphorus. Again, the body uses electrolytes to help regulate nerve and muscle function and acid-base balance. To function normally, the body must keep the concentration of electrolytes in its compartments within very narrow limits. The body maintains the concentration of electrolytes in each compartment by moving electrolytes into or out of the cells. The kidneys filter the electrolytes in the blood and excrete any excess in the urine to maintain a balance between daily intake and output. If the balance of electrolytes is disturbed, disorders can develop. An electrolyte imbalance can occur when a person becomes dehydrated, uses certain drugs, has certain heart, kidney, or liver disorders, or is given intravenous fluids or feedings in inappropriate amounts. Now that we understand the role of electrolytes and the importance of equilibrium in fluids and electrolytes, let's discuss the next factor for homeostasis, acid-base balance. Acid and base balance is the third component involved in maintaining homeostasis. For simplicity's sake, we have discussed homeostasis in individual compartments, fluids, electrolytes, and now acid-base. However, in actuality, all three are interrelated. Let's begin by defining acids and bases, then we'll discuss how to maintain a proper balance. To do this, let's take a trip back to high school chemistry class. An acid is a substance that releases a hydrogen ion when it's dissolved in water. A base is a substance that accepts a hydrogen ion when it is dissolved in water. In other words, it will bind to a hydrogen ion. The pH scale is the method we use to describe a solution's tendency to give up or accept hydrogen ions, or it is how we classify a solution as either an acid or a base. The pH scale ranges from 0 to 14. Values from 0 to 7 are considered acids, and values from 7 to 14 are considered bases. Water is a 7 and is considered a true neutral. Various body fluids have a wide range of pH values. Gastric juices can range from 1 to 5 and are considered acids. Pancreatic juices can range from 8.4 to 8.9 and are considered bases. Blood ranges from 7.35 to 7.45 and is considered neutral to slightly basic. While it is important to maintain certain ranges for each type of body fluid, the focus of the rest of this presentation will be on acid-base balance of blood, specifically that of arterial blood. Remember, the normal range of pH for blood is 7.35 to 7.45. These values fall in the neutral range of the pH scale, but when analyzing blood values, any value less than 7.35 is considered acidotic, and any value greater than 7.45 is considered alkalotic. There are several components that are involved in the maintaining of proper pH balance of blood. For instance, many electrolytes help to control pH balance. Again, for simplicity, we'll discuss the two main components in balancing pH balance. Those are carbon dioxide and bicarbonate. It is the amount of carbon dioxide and bicarbonate that determines the pH and ultimately determines if the blood is acidotic or alkalotic. Carbon dioxide is thought of as an acid. An increase in carbon dioxide will cause the blood to become more acidotic, and thus the pH value will decrease. Conversely, if the levels of carbon dioxide decrease, the blood will become more alkalotic and the pH will increase. Let's visualize this with the help of this scale. One side is carbon dioxide and the other is bicarbonate. In order to have homeostasis, there must be balance of the scales. If you add more carbon dioxide, the scale will tip towards acidosis. If you take away carbon dioxide, the scale will tip toward alkalosis. Bicarbonate is thought of as a base. If the amount of bicarbonate increases, the blood will become more basic or more alkalotic, and the pH will increase. In other words, if you add bicarbonate to the scale, it will tip toward the alkalosis side. If you decrease the amount of bicarbonate, the scale will tip toward acidosis. The blood will become acidotic and the pH will decrease. Now, let's look more closely at these components. Both carbon dioxide and bicarbonate act as buffers. A buffer is basically a substance that helps to keep the pH normalized between 7.35 and 7.45. They can act immediately by either releasing hydrogen ions or attaching to and thus removing hydrogen ions. This is important because the buffer action counteracts forces that tend to make the blood either too acidotic or too alkalotic. If a strong acid is added to blood, it will combine with bicarbonate to ultimately form carbonic acid, which has a low free hydrogen ion concentration. If a strong base is added to the blood, it combines with carbonic acid and stays more neutral. This part is a bit technical, but what you really need to remember is that carbon dioxide acts as an acid and bicarbonate acts as a base. The normal value of arterial blood carbon dioxide is 35 to 45 millimeters of mercury. Now, what happens to the pH level of blood if the carbon dioxide is increased to 50? Think back to that scale. If you add carbon dioxide to the scale, it will tip towards acidosis. Another way to remember this is to think of the inverse relationship between pH and carbon dioxide levels. Since an increase in carbon dioxide will cause an increase in acidosis, there will be a decrease in the pH levels. Thus, increases of carbon dioxide cause a decreased pH, and a decreased carbon dioxide causes an increased pH. Carbon dioxide is essentially controlled through the respiratory system. During increased respiratory rate, as seen in hyperventilation, the body will blow off carbon dioxide, so there is a decrease in CO2 values. This will lead to an increased pH. The opposite occurs when a person has very shallow and slow respirations. The body will retain carbon dioxide and cause the pH to decrease. So, if a person is hyperventilating, the CO2 can decrease to 28, causing the pH to increase. And if a person is experiencing depressed respiration states, the CO2 can increase to 49 and the pH will decrease. The CO2 respiratory buffer system responds fairly quickly. When the brain senses an increase or decrease outside the 7.35 to 7.45 range, it can signal the respiratory system to increase or decrease respirations to help the pH get back to or stay within the correct range. The second buffer system, bicarbonate metabolic, may take several days to respond. The normal bicarbonate level for arterial blood is 22 to 26. Looking back at the scale, if you add bicarbonate, the scale will tip towards alkalosis, and if you delete bicarbonate, the scale will tip towards acidosis. If you like the visual of comparing the relationship of bicarbonate to pH, you must remember that bicarbonate and pH rise and fall together. In other words, an increase in bicarbonate will cause an increase in pH, and a decrease of bicarbonate will cause a decrease in pH. The HCO3 buffering system is more complex than carbon dioxide's buffering system. The bicarbonate system is controlled primarily through the kidneys and is influenced by the interaction of the electrolytes. The kidneys can control electrolytes to help control pH values. Remember, electrolytes have either a positive cation or negative anion charge. The kidneys can hold on to cations and exchange them for hydrogen ions, then excrete the hydrogen ions and thus increase the pH levels and make the blood more alkalotic. This is a very, very complex mechanism and requires many interactions. For these reasons, it is not as immediate as the CO2 system and may take several days to become effective. Let's pull all of these concepts together and analyze some ABG results. In this example, the pH is 7.28, the bicarbonate is 25, and the carbon dioxide is 49. Is the pH above normal range, below normal range, or within normal range? The correct answer is B. With a pH of 7.28, it is below the normal range of 7.35 to 7.45. Thus, we know that it is acidosis. The bicarbonate is within the normal range of 22 to 26. What does the carbon dioxide reading show us? CO2 is within normal range. CO2 is too high, or CO2 is too low. The correct answer is B. The CO2 is above the normal range of 35 to 45, which tells us that the problem is respiratory based. Since it is the respiratory system that controls the carbon dioxide, we can label this as respiratory acidosis. It is acidosis that is caused by the respiratory component. We can double check this by looking at our arrows. The pH is decreased and the CO2 is increased. Is this what you would expect? Absolutely. Remember, there is an inverse relationship between pH and carbon dioxide. What then are the causes of respiratory acidosis? Well, most likely this person has a very slow or shallow respiration pattern, which is causing a retention of carbon dioxide, thus decreasing the pH. Let's try another example. Here the pH is 7.49, bicarbonate is 30, and the carbon dioxide is 38. We can see that the pH isn't normal. The 7.49 is above the normal values of 7.35 to 7.45. What does an increase in pH value mean? Alkalosis or acidosis? The answer is A. This is a state of alkalosis. What about the bicarbonate value? What is normal for this HCO3? Is it 18 to 20, 22 to 26, or 27 to 31? Normal is 22 to 26, so this reading of 30 is an increase. Knowing what we do about the relationship between pH and HCO3, we can determine that this patient is in a state of metabolic alkalosis. It is alkalosis because the pH is above the normal value, and it is metabolic because it is the bicarbonate, which is the metabolic component that is causing the deviation. A very common cause of metabolic alkalosis occurs when the patient is vomiting and has diarrhea. It is also seen when a nasogastric tube is inserted and there are large quantities of drainage. Earlier, we identified that gastric fluids are very acidic, with a pH that can range from 1 to 5. When large amounts of these fluids are lost, there is an imbalance within the metabolic components, which leads to an ultimate increase in bicarbonate. This occurs through the various complex interactions between the electrolytes, hydrogen ions, and bicarbonate. This will eventually lead to an increase in the pH of the blood or alkalosis. So how do we go about balancing values once they get out of sync like the two examples we've seen? This is where things can get very complex. All you need to remember is the two mechanisms that cause acidosis or alkalosis are respiratory and metabolic. The respiratory processes are reflected in the carbon dioxide lab values, and metabolic processes are reflected in the bicarbonate lab values. Now that we've reviewed the causes of acid-base imbalances, we must now turn our attention to compensatory mechanisms. Remember our scale. You can change pH by increasing or decreasing either CO2 or HCO3. If you are adding CO2, the scale tips down towards acidosis. The goal of homeostasis is to keep that scale balanced. To balance the scale, in this case, you can either delete CO2 to relieve the burden on the acidosis side, or you can add bicarbonate to even out the scale. In this case, the system causing the imbalance is the respiratory system because there is an increase of carbon dioxide, and it is the respiratory system that controls carbon dioxide. You can't expect the respiratory system to compensate itself. What occurs is that the metabolic system will kick in to correct the imbalance. How does this happen? The only option is by adding more base or bicarbonate to bring the pH back in balance. If we look back at our previous examples, we can determine what the compensation will be. This is an example of respiratory acidosis. We can't expect the carbon dioxide to correct itself, so what will bring the pH back into normal range? An increase in HCO3 or a decrease in HCO3. A is correct. We need to increase the bicarbonate, which will add more base into the blood and bring the pH back into normal range. The kidneys will control this through many complex reactions based on the reabsorption and excretion of various electrolytes. As a reminder, since this compensation is through the kidneys and involves many interactions, it will take some time for compensation to occur. The second example we discussed was an example of metabolic alkalosis. This is an example where there is too much bicarbonate and the scale is tipped toward the alkalosis side. How can this be corrected? We can either remove some of the bicarbonate, which will relieve the load on the alkalosis side of the scale, or we can add some carbon dioxide and acid. This would add load to the acid side of the scale and ultimately balance both sides. In this instance, the bicarbonate cannot correct itself by getting rid of the excess bicarbonate, so the respiratory system will kick in to compensate by adding extra carbon dioxide. What happens when we increase the level of CO2 in the blood? When the acidity will bring back the pH into normal range. When pH values move outside the normal range of 7.35 to 7.45, the body can suffer very ill effects, even death. Thus, homeostasis is essential to survival. The amazing thing about the body is that there are built-in compensatory mechanisms. For pH balance, the compensatory mechanisms are the two components we've spoken about: respiratory and metabolic systems, or carbon dioxide and bicarbonate. These two systems are intimately intertwined. A change in one will automatically lead to a change in the other. In a perfect world, these changes are occurring on an ongoing basis, and there is minimal change in the overall pH balance. Occasionally, there is an illness, injury, or stress on the body that causes an imbalance to occur. If the imbalances become too great, medical intervention may be necessary and include medication, procedures, or mechanical ventilation. As a healthcare provider, part of the care of patients includes an assessment of the patient and his or her blood gases. It can seem a daunting task at first, but with practice, the analysis becomes easier. As a reminder, here are a few important steps in fluid and electrolyte analysis. First, look at the pH. Does it fall within the 7.35 to 7.45 range? If so, it is within normal range. If it is less than 7.35, it is acidic. If it is greater than 7.45, it is alkalotic. Second, determine the cause. Remember, carbon dioxide has an inverse relationship to the pH. If there is an increase in CO2, there will be a decrease in pH and vice versa. The opposite is true of bicarbonate. An increase of HCO3 will cause an increase in the pH, and a decrease in the bicarbonate will cause a decrease in the pH. And finally, compensation is accomplished by the component that is not causing the original imbalance. If there is too much carbon dioxide causing the blood to be acidotic, it will be compensated by an increase in the bicarbonate to bring the values back within normal range. That's the conclusion of today's program on fluid and electrolyte imbalance and overview. Check your listings for the follow-up to this presentation, focusing on the cause and assessment of fluid and electrolyte imbalances. Keep shaping the future and have a great day.